Okay, hello. So my name is Karel Durkota, and I'm going to present our collaboration between CTU in Prague and Avast on a topic that not all anomalies are equal, a game-theoretic approach to adversarial anomaly detectors. And this was done in, the co-authors are me, Petrova, Alperovic, Horák, Boshansky, and William Lissi. So the main motivation of our project is, again, that if you train a machine learning classifier and deploy, for example, to classify dogs, to tell apart dogs from cats and deploy it into the wild, of course it will continue working well because dogs and cats, they don't change their appearance in order to fool the classifier. However, this is not true in the security domains where the opponents are adversarial. And so basically how it usually works is that we train a classifier to detect some malware, deploy the model, attackers learn how to avoid being classified, they develop new attacks, then we learn their new attacks and we retrain classifier and deploy it again. And the whole process repeats on and on. And so you can feel that there is some game emerges here, and so that's why we decided to use game theory actually to model this interaction between those two players. So let me go through a running example on a data exfiltration problem to show you what we're dealing here with. So imagine there is a user that on a daily basis uploads some data to the internet, and we can learn statistics, how often he uploads how much data, megabytes per minute. So this is something known to, let's say, administrators of that company or network. And now let's say that the computer has been compromised by an attacker whose aim is to exfiltrate as much data as possible from that host. So basically, attacker, for different actions, we can imagine his reward functions to be this red line. So if attacker in next minute or time step doesn't upload anything from that computer, so his reward is 0. However, if he uploads 50 megabytes per minute, so he will obtain some higher reward. And so now we can reason what would a rational attacker do in next step. So obviously he would exfiltrate as much data as possible. So with this thinking, and we can develop some easy classifier. So we just come up with some threshold that if from that host is more data uploaded in next time step than 36 megabyte, so we will raise alarm, and that computer is going to be inspected by the administrator, and if attack is present or attacker present there, we would detect him and his attack is ceased. And so by developing some threshold, computing some threshold, we also we will have some false positive rates, which are the false alarms, because even the user, without being compromised, from time to time, he may upload 40 megabytes per minute. And so this we assume to be a constraint in our approach, that we don't want to have more false alarms than 1%. OK, so given that actually we can compute this threshold with this 1% false positive rate, attacker could counterattack to us by playing new maximum for him, which is 35 megabytes per minute. So it's just below the threshold. And again, we can counteract his action by for example, having two thresholds. So one threshold to inspect or raise alarm with some probability actions when from user are uploaded megabyte per minute in this range. So then we raise alarm with probability 0.3. So that way we decrease the expected utility for the attacker by a factor of 0.7. And if the user's behavior is in this range, so we will raise alarm with probability 0.9. So now again, we decrease attacker's utilities here, but there is new maximum for the attacker, so he would play that action. So we could counteract that action again, so we can develop another threshold. And if you play on and on this game, we could actually compute a continuous distribution of probabilistic thresholds how to inspect or raise alarms in such a way so that the attackers at maximum is kind of constant here, and here he is detected with probability 1, so he doesn't get any reward. And the important is that this classifier still has false positive rate only 1%, the same as all the previous one. And by changing anyhow this probabilistic classifier, for example, we could reduce attacker's utility by moving everything to the left, but that will increase the false positive rate. So this classifier is, in some sense, optimal what we can get with this constraint. So let's get back to the context where we are. So standard anomaly detectors work as a black box. It obtains a set of data, and it creates boundaries around sharp boundaries, what is anomaly and what is benign, or what is nominal data. If we add false positive rate constraints, so it will scatter around, usually unsystematically, where are the false positives. So in the adversarial anomaly detector, we additionally provide a reward function for attacker's reward function. And so in this case, attacker has high reward towards the right region of the feature space and lower reward here. So therefore, the adversarial anomaly detector will inspect, so it will shift all the false positive rates to the region where attacker has higher reward. So therefore, even though usually this is benign point, but if attacker was to play, so he would probably play here. So let's inspect those samples from time to time as well to reduce the attacker's reward. And so these work better than the previous non-informative about the reward, the attacker's reward methods. However, so this case was studied by Dritsula in 2017, and so there is one drawback that this assumes that for given attacker's action, we actually know where it lands in the feature space, and we know the exactly reward function of the attacker for each of his actions. However, the problem is that it might not be true, and therefore we developed a generalized adversarial anomaly detector, which I will present here. It's highlightly. So the motivation is why we don't observe those actions is, let's assume this example that we see 40 megabytes per minute as the next sample in the next minute that was uploaded from that user. However, we cannot tell whether it was user who uploaded 0 megabyte and attacker exfiltrated 40 megabyte. Therefore, based on this attacker's action, we know that we should inspect it with probability. I'm sorry, these numbers are swapped. So with high probability because there is strong reward for the attacker. Or it was user who uploaded 40 megabytes. Attacker actually didn't do anything because that computer might not even be compromised. Therefore, we should not inspect it at all. So here should be 0, and here should supposed to be high inspection probability. And so this uncertainty introduces high complexity. Actually, how should we solve this problem? How should we inspect the different actions? Because we don't know actually the attacker's reward when we see the observations. So our approach is that we model the interaction between these players as a game. So defender, us, we choose a classifier so that we minimize the expected utility for the attacker. An attacker chooses attack vector that maximizes his expected utility. And the expected utility we compute as for the attacker that he is not inspected, not classified as anomaly, times what is his reward for the action. And additionally, we have a constraint that false positive rate of our classifier on benign data should be below 0.1 or whatever. That's an input. And we are given two functions, the reward function for the attacker and distribution of the observations that we as a defender observe given that attacker chooses an action to play. So our algorithm, which is a value-based approach, so the key insight of the algorithm is that given that we know the value of the game, which is maximum that attacker could obtain against optimal classifier for any action that he could play. We know that any attacker's action A, we should inspect with this probability. That's based on the reward for the attacker. And so our algorithm does the following steps. It computes attacker best response action against our initial random classifier. Then we sample many observations from the observation function. And we know that in average, those observations we should inspect with this probability. So we train neural network to inspect those all observations in average with this probability. And then, based on the error of the neural network, whether it was able to train well or not, we update value of the game. And then the whole process repeats until the whole algorithm converges. So let me show one preliminary example. We took a problem of data exfiltration through DNS requests. So your computer on a daily basis does many DNS requests, and when attacker compromises your host, so he uses those DNS requests to exfiltrate data. And so we took 20,000 DNS requests, which we assumed to be benign, and we used that data set to train 5 different classifiers. So VBA was ours, and actually we trained 20 standard anomaly detectors. Here we show just the 4 best performing. And then we computed how much attacker could exfiltrate against those classifiers with the best action he could actually play. And so in our case, attacker was able to exfiltrate 22 megabytes, and other approaches, it was, so PCA actually performed quite well. It was 55, and the others were worse. So in this case, optimal is actually not 0, or we don't know what is the optimal value. Maybe actually this is the optimal, but we assume that even against the best classifier, there is some attack that attacker can perform and still exfiltrate some small amount of data. So optimal might be 50, not sure. So the potential applications of this research is that we could apply this adversarial anomaly detection to detect whether there is ongoing data exfiltration over Dropbox, on Google Drive, or even through net flows. So we can inspect the net flows to see if there is data exfiltration. Also, we could detect credit card fraud detections this way, or compromised accounts on social media, and more. So in this research, we developed, as a conclusion, a value-based approach which generalizes the previous algorithms. So first, it drops the assumption that we know the attacker's reward and his for each action. And also, on previous algorithm that we worked on, so it discretized the whole feature space and computed linear programming over that. So it worked fine as well. However, the discretization usually is not a good approach, because with the number of features, the discrete steps in the problem increases exponentially. So we were able to solve like 3 featured space. And with the VBA algorithm, we can scale up to 20, 30 dimensional feature space. And so the paper is now under review on AAAI. And so main takeaway from this is that when we count with the game theoretic approach, so we may perform better than non-game theoretical approach in the adversarial environment. And so the anomaly detectors, the standards, may find actually suboptimal solutions. And second takeaway is that not all anomalies are equal. So if you have any questions, get in touch with me. I'll be here. So thank you.